Okay, so again, your equation, a general second order equation with constant coefficients in this case, with positive B and positive C, turns out to relate to motion with a linear drag force and a linear restoring force. Okay? Also, to the behavior of an RLC circuit, resistor, an inductor, and a capacitor. Okay? Now we haven't quite gotten to the capacitor part, the inductor part of physics, but we've done a lot of things with inductors, so it's going to be pretty easy to understand, at least conceptually. Because what's an inductor do? An inductor is like a coil, or it could be like that cylinder we're dropping the magnet through. Okay? You get an EMF around the coil, which creates a current around the coil, which creates a magnetic field opposite to the one of the magnet that's dropping, which is why the magnet drops slowly. Okay? Well, we put that inductor into a circuit. Okay? Of course, with the copper, you'd have to, cut it along one edge and insulate it, so you, and then connect each edge to a different part of the circuit. Interrupt the circuit with the thing, with the connection to each edge. Okay, so this current has to go through that cylinder. Okay, now it's really better done with a coil or a solenoid, which is just a coil over a certain length, slinking. Okay. The geometry is very similar, and we're inducing a current, okay? And the thing resists the buildup of a current, because in order to build the current, you got to change the magnetic field, okay? You change the magnetic field within the inductor, and that magnetic field itself opposes the increase of a current. It's a step beyond what you've already seen, but only a step. And you'll understand it soon. Okay, so anyhow, this equation can represent either. Now, in the case of a mass, linear drag force divided by mass. That's this. Okay? And this is your linear restoring force divided by mass. Okay? Now, initially when you set the thing up, you'd have like an my double prime plus a gamma y prime plus a ky, okay? But then you divide through by the m and you get a b and a c, and this is 1. So I'm going to treat it like that because it's really easy to see. Just to amplify and reinforce what I think I've already done. Okay, so right, we agree that depending on this discriminant, we get 2 real solutions, a repeated real solution, or a complex solution. And a complex solution could be purely imaginary, okay, which automatically happens if b equals 0. Now the significance of that would be you have no drag. So you just have motion with a linear restoring force, and you have a purely imaginary solution, an e to the I theta. This is a combination of cosine of omega t and sine omega t. Okay? And we've worked through the details of the complex solutions combined. Okay? Now interpretation. B equals gamma over M, C equals K over M, okay? And gamma is your drag coefficient, K is your restoring force constant. You're used to K from physics and what we've already talked about here. We've talked about gamma, okay? To get complex conjugate solutions, exponentially decreasing oscillations, if B squared is less than 4C, which comes down to gamma squared is less than 4K. There's something wrong about the constants there. Or does gamma have those?
What's a conjugate solution?
Complex conjugate solutions, that's your plus or minus on your imaginary.
Okay. What does conjugate have to do with it?
Huh?
What does conjugate have to do with it?
The plus and the minus give you conjugate solutions.
Okay.
Okay? It's algebra 1. It's been a while. If you haven't seen the term, well, it should be a familiar term if you're reminded about it. And if it's not, make it familiar. Okay? Quadratic equations. As soon as you learn quadratic equations, as soon as you start doing complex valued solutions, you immediately see the terminology complex conjugate solutions. It's basically late algebra 1 or early algebra 2 if the courses are taught the way they're taught in most of the world. Actually, it's pre-algebra in most of the world. Okay? Not putting you down for not knowing it, just pointing out. I don't know how you got this far without knowing that. Okay? Certainly you can do the arithmetic with it. That's not a question. So the terminology, I don't know. Anyhow, you get this? I'm sure you understand that little more. Recreate it when you need to. Okay? And I said my units were wrong here because I was being somewhat ignorant. It should be gamma squared over m squared less than 4k over m. So that's gamma squared over m less than 4k. Or if you prefer gamma less than 4k m. Okay?
Wouldn't you have an imaginary number? Like it would be I, B, or I sinus beta?
Yeah, I didn't write it down. I should go back to pre-algebra and learn to write these things down.
Let's do it together.
Okay? I've got an excuse. 50 extra years to expand my depth of knowledge and contract my ability to do clerical things. Okay. So you can watch me in the clerical stuff, but concepts are there. Okay. Okay. Yeah. You should be able to work out these details. I'm not too worried about that. although I need to be more careful. I need to figure out how to do that. Got to slow myself down a little bit. It's hard to do that when I'm enthusiastic. Okay. I mean, that's it. Okay? If your drag force is too great, then when you release that pendulum or that mass on a spring, it's never going to pass equilibrium. Okay? If it's a little smaller, then it'll pass equilibrium, not get too far on the other side. Come back, a little on the other side, and then you lose energy in the oscillations. If you have just a very small gamma, it's like a pendulum in air. It just keeps going for a long time. But it does lose energy, also because of the flexion of the string and stuff. Okay? You can't get that kind of friction out of it, but if you engineer it carefully enough, you can keep that to a minimum. Probably do a physical pendulum with a rigid string, which then no longer be a string. Okay? And then you're just, you put your differential equation. Be theta double prime minus torque. Okay? Moment of inertia times theta double prime is equal to a negative multiple of position, and that's torque equals torque. Okay? So you should be able to generalize simple harmonic motion. Equations are identical. You're just talking torques and moments of inertia rather than forces and masses. Now that's a digression. But this would apply there too, equally well. And you'd have your torque, you'd have a drag torque coefficient, okay, as a multiple of the angular velocity. The drag torque is a multiple of angular velocity. Okay, well, that said, there it is. There's the picture. We've already talked about it. Now for circuits, Y is now Q, which is the charge on a capacitor. The rate at which the charge of the capacitor changes is the current. Y double prime is, well, you don't know. Okay, it's the rate at which, it's proportional to the rate at which current is changing. In a coil, that's proportional to the rate at which the magnetic field is changing, which is what gives you an EMF that opposes the change in the current.
So Y double prime is proportional to the flux?
Well, when you get down to the details, but Y double prime is Q double prime. Okay? And its rate of change of current, which is proportional to rate of change and I'll say a coil, through a coil, okay? And we'll distinguish coils from solenoids later. It's fairly simple once you have the underlying concepts. Okay, and no, we'll do this mathematics. Okay, so it's the rate of change of current, which is proportional to the rate of change of the magnetic flux through the coil, which is proportional to opposing EMF. Okay? So,
I got those last two problems right now. I forgot how to do.
Oh yeah.
I still don't really know how to do it.
I'll write it like this. I'm not going to go in all the detail because we're not quite there in physics yet. We haven't defined capacitance, but it's simply the ratio of charge to potential difference across a capacitor. Okay. We haven't talked quite in enough detail about capacitors, but we've had problems. We've solved differential equations for capacitors. Okay? I think you've solved them. I don't know. I'm not sure I've seen them from everybody. But, no, I've seen at least two. Okay, so anyhow, that's what you have. Well, your opposing EMF is L times Q double prime, where L is inductance. But all we said is Y double prime is Q double prime. It's the rate of change of current. It's proportional to the rate of change of magnetic flux, which is proportional to the opposing EMF. Well, that's just your proportionality constant. Okay? So you multiply that by the second derivative of your charge, which is a derivative of your current, and you get the opposing EMF. Okay? R is just another constant related to conductivity and stands for a word you're not allowed to use yet.
So it's not Reinberg's constant? However you say that.
What?
So it's not the constant, the universal constant R?
No.
Is it
But that's a good question, okay?
resistance?
Shh. We talk about energy and conductivity. The V word and the R word are not yet part of our physics vocabulary, so I'm not going to use them here. But we'll be using them soon. Okay? Now, this equation is just Q double prime plus R over L Q prime plus Q over LC equals 0, and that's just this equation. So now B is R over L, C is Q over L times capital C, okay? And we get an oscillating solution if B squared is less than 4 times little c. That is okay. R is analogous to drag, making you think of that electrical R word, okay? Which is got a reciprocal relationship with that mechanical R word when you crank the generator, okay? So if R is really small, you just get a forever oscillating solution, just like you do. So you have, you know, like a superconducting circuit can oscillate, okay, for a long, long time. Now, if you got a little bit of this R word in there, then the oscillations gradually decrease, right? Of course, you can make the equation non-homogeneous by giving this thing a boost every 3 microseconds or whatever it is. And then you have a non-homogeneous equation. It behaves no differently than any other non-homogeneous equation we've ever seen. Okay? Drive it with a square wave, well, you're going to have to use Laplace transforms. Okay?